And so we'll look at this function, an arbitrary function that goes from a to x, and we can define the average rate of change from a to x as going from, as the difference quotient, where you say f at x minus f at a divided by x minus a, and we get the slope of that secant line. That's the purple line. And so then if we define that difference of x to a as h, remember earlier I've used either delta x or something like that, but I'm going to start using h now, just because it's easier to write more than anything else. We know that x equals a plus h, and so then our function, that f at x is actually f at a plus h. Okay, all those things are equivalent now. So instead of saying x, I'm going to say a plus h, and instead of f at x, I'm going to say f at a plus h. And so that difference quotient then just by substitution turns into f at a plus h minus f at a over h. And then as we make that average rate of change closer to the point a, what we get is an instantaneous rate of change, and we're going to define this as the derivative at that point. So you can see that as I'm moving that, if I make h smaller, I'm moving that point closer to a, and so f at a plus h gets closer to f at a, and we ultimately end up with the secant line. The limit of that secant, the slope of that secant line is going to be the tangent line. So this is that definition, that f prime at a equals that limit. That's something that you should commit to memory. It's one of those fundamental definitions in calculus that you should know. Okay, so to review the example that I gave earlier, let's say we have the function f at x equals x squared. And I want to calculate the slope of that thing at 1. So what I'm going to do is I'm going to pop it into my definition, where as h goes to 0 of f at 1 plus h minus 1 over h. And so just by substitution, I'm going to insert 1 plus h into the function, and then 1 into the function, take the difference, divide by h. And so just through algebra, I'll expand that 1 plus h squared into 1 squared plus 2h plus h squared. And then I notice that I have a 1 squared minus 1 squared, so those drop out. And then I have something that involves an h term in all of them, so if I factor out the h in the numerator and then cancel out the h's, I get 2 plus h. And so as h goes to 0, my limit is 2, and therefore my my function, the derivative of my function at 1 is going to be 2. So if I drew this out really carefully, and I try to draw a tangent line at 1 for x squared, we're going to find that that slope is going to be 2. Okay, so once we have the slope, and we also know what point that we're going through, we can find the equation of the tangent line. Now later on we're going to use this to estimate values that are close to our function. Sometimes we want to do that. It's called linearizing our function. But if we just look at what we have, we know that the derivative at 1 is going to be 2, and the function itself is going to be 1. There's that line. And so in the point slope form of the line, I have everything I need now. I have x1, y1, which is 1, 1, and then I have m, which is going to be 2. So if I just make my substitutions, what I ultimately get then is the equation y equals 2x minus 1. And so that's the equation of the tangent line. So I got it by calculating the derivative at the point, it gives me the slope, and I know since the tangent and the function coincide at the point that I'm taking the derivative, I have my point and I have my slope, so I can do that. Okay, so let's look at a different example now. Let's say we want to find the derivative of this function at 1, where it's just 1 over x. Okay, we do the same process where we make the substitution where we have 1 over 1 plus h minus 1, and we'll find the common denominator. And so the common denominator is going to be 1 plus h, and so if I multiply the numerators appropriately, where the left-hand term, that 1 over 1 plus h, the 1 stays unchanged. When I'm subtracting the 1 on the right, then I multiply that by 1 plus h over 1 plus h. And so I get that, that ratio that you see there. And so by simplifying this then, I notice that my 1's cancel, and I'm going to combine the fraction. You all should be kind of familiar, not kind of, but you should be adept at dealing with complex fractions to make it a simple ratio. And so when I'm looking at my limit as h is going to 0, I notice that I can cancel out an h again, and so what I get is negative 1 over 1 plus h. And as h goes to 0, we get a slope of negative 1. Now you'll have a number of these to do, and they're a little on the tedious side because you're calculating this limit, and it always involves some type of expansion and trying to eliminate some terms so you get a ratio that is equivalent to the initial expression that you have. If you try and evaluate the initial expression, you virtually always get 0 over 0. And so this is an equivalent expression there that kind of includes that one point that's missing in the domain from the function by simplification.
And these we're going to do on WebWork.
These will be on WebWork, yes. Okay, so far I've taken a point A, and I've calculated the derivative of this thing at A. And I've assumed that A is a constant. Now, so I've found the derivative at that point. Now, if I just take all of A's, if I take my whole domain and just leave it as x, I actually can get a function that is the derivative. All right? So if we use the same definition where we're using x instead of h, I can get to the same thing. So let me do that, that derivative of the same function that I just did, but instead of doing 1 over a, or trying to find f prime at 1, I'm going to try and find f prime at x. And you'll find that the process is exactly the same. In fact, the algebra is exactly the same. Instead of a 1, you have an x. And so one of the things that you can do, but you have to be kind of careful about this because frequently it's easy to drop that limit thing in the front. You just keep on making equivalent expressions for what you're trying to find the limit of. And so that's a lot of writing. What you can do is take the expression here and just take that out, and then the task here is just to simplify this, and then once we do that, I'll insert it back into the limit to calculate the limit. So in other words, I'm not forgetting to write the limit, I'm purposely writing my expression outside of the limit so I can simplify it and do a little less writing. So on this particular one, the algebra works out just the same as we had before, where we get the first x minus x makes that x disappear, and then we have a negative h over h, and that cancels out. And so I have this expression 1 over x times x plus h. And so when I go back into the limit form of this, if I find the limit as h goes to 0, what I'm going to get is negative 1 over x squared. So now I have a function that any point that I want to find, I'll find the derivative. So remember from the last slide we calculated f prime at 1, and we found that that was negative 1, right? So if I put in a 1 in my negative 1 over x squared, I'm going to get negative 1. So this is you can find the general equation for the function, and then at any point, if you need to determine what the derivative is, what the value of the derivative is at a certain point, you just plug it into this function. So let's look at it from a graphing standpoint. Okay, the black line is 1 over x. And if I graph negative 1 over x squared, what I have is this graph superimposed on it. So you can kind of read off that where you have, let's say right here, where my f at 1 is, my slope at that point is going to be negative 1. So if you were to, you know how you did those graphs of derivatives from not knowing the function? Now we have a way, if we know what the function is explicitly, to figure out exactly what that derivative looks like. So we'll be doing it analytically rather than kind of qualitatively from here on. Okay, so let's look at a derivative as a function with a little bit more complicated function. And when you get into powers, remember the general strategy of these things is to expand it. So these will get a little bit unwieldy. Oh, it's doing that. Okay, so I'm going to first substitute x plus h into the function, so I get those first two terms, x plus h cubed minus 2 times x plus h. And then I'm just going to have the function with x, which is minus x cubed minus 2x. When you're doing these, I would suggest, particularly for the back half of this thing, back here, where you're taking negative f at x, is to keep this in parentheses so you don't have to, when you're first writing this out, think, okay, I'm going to have a double negative, so that thing goes to positive. Because you almost always, at least I shouldn't say you, I almost always mess up if I don't do this. Put things in parentheses, write it all out, and then worry about how the signs cancel each other. So the first thing I'm going to do is expand that first term, and then expand the second term, and then subtract the last term by treating the signs appropriately. So I have a negative x cubed plus 2x for that function f at x. And so I have all these things. And you notice here that I have an x cubed and a negative x cubed, and then I have a negative 2x and a 2x in there. So if I eliminate those, I'll get this expression here, and everything involves an h. So if I factor out an h, then I'm just going to get this particular polynomial here. So I'm going to calculate the limit as h goes to 0, and all I'm going to end up with then, because that middle term is going to go to 0, is I'm going to get my derivative is going to be 3x squared minus 2. Oops, sorry, that was a little faster than I intended. Now, I want you to notice something. On this polynomial, we have x cubed there, and the x cubed is, the derivative of that is going to be something in x squared. And this is, you're going to find that this is going to be true, that any polynomial, whatever degree it is, that the derivative is going to be a degree of one number less. And in fact, we're going to come up with a rule that will allow us to calculate derivatives very, very quickly. And if you look at that first one, find the derivative of x cubed minus 2x, that's going to be a very easy, quick thing to do. And if you kind of notice the pattern here, we have the coefficient of 3, and the derivative is the exponent in the original function. And so next week we'll be laying out all those kinds of rules, and we won't be doing this big long calculation of the limits after this. Okay, so let's talk about some alternate notation for derivatives, because we're going to be doing some different things with derivatives, and so we want a couple different ways to write it. Now, in the history of calculus, calculus started back in the time of Sir Isaac Newton, you know, the guy with the apple and gravity and that kind of stuff. he was insanely smart, and he contributed to so many things. If you're taking physics, you know Newton's laws of gravity and things of that sort. He was one of the inventors of physics, of calculus. Another guy who was the inventor was a German by the name of Leibniz. And depending on whether you're British or German, you will say either Newton or Leibniz invented calculus. And in reality, they both did at the same time. And they both came up with slightly different notation. Okay, so, and both of the notations are useful. So what we've seen so far is that we have this f prime at x denotes the derivative. The other thing that we can do is just say y prime. Now, when you get into differential equations, it's going to be very cumbersome to always write f prime at x and all this kind of stuff. So we just leave off the x. We just assume that it is a function of x. And so it's perfectly legitimate to write if your function is y equals 2x plus 1, the derivative can be written as y prime equals, and then in this case it would be 2. And then another, and this is Leibniz notation here, is dy dx, all right? Now, d isn't a variable, it's an operator. It's intended to mean the differential of y over the differential of x. And I'll explain that a little bit more, where that comes from and what it relates to. We don't have to always write dy dx. We can write df dx. Here we're suggesting that f is the name of the function, and so we're not writing the at x part, although it's perfectly good to write it like this. So this d dx is going to be the way that we indicate that we're going to take the derivative of f at x. So, you know, just like when you're doing some algebra on an equation where you add 1 to both sides, or you multiply both sides by 3 or something like that, well, we want to take the derivative of both sides of the equation. That's what we generally write, that we can just write this operator right in front of both sides, and then we go ahead and differentiate things. So that's, you usually see this notation kind of in an intermediate calculation, and then you're ultimately going to label it either this or this. Now there's two other notations that we have. One of them is the capital D f at x, and the other one is d sub x at f at x. And the reason why they'll use a sub x is because later on you can talk about functions, multivariable functions, where you have to specify what derivative you're taking. If you're taking, you know, if you have a function like xy plus 2y squared plus 2x, you can take the derivative with respect to y or with respect to x. And so we're not going to do it in this course, but you're going to see it sooner or later, that this differential operator here, capital D, is exactly the same thing as this differential operator d over dx. Okay, so we're not going to use it in this course. Don't really worry about it too much, but once you see it, recognize that it's just a different way to write the same thing. Okay, so this dy dx you can think of as the limit of delta y over delta x as delta x goes to 0. And so we're going to be using these things. We're going to be using delta y over delta x as the slope of the secant line, right? Because delta x and delta y are finite values. The differential values are the values that as delta x goes to 0, dy dx is what that's going to equal. So this one here is, whoops, wrong pointing. This one here is the slope of the secant line. This here is the slope of the tangent line. And so as you bring that difference here to 0, you're going to get the secant line to coincide with the, or nearly coincide with the tangent line. You're going to get it as close as you want. Okay, two other things to notate. Sometimes you want to evaluate a derivative, and so the way we do that, of course, with the notation that we used before, is we just say f prime at a, so where a is a number, okay, like we've used f prime at 1. The way we notate it with Leibniz notation is that you're going to make this vertical line, and then at the bottom you're going to say x equals a. So that means it's the derivative of y with respect to x at a. So this is an evaluation. So dy dx implies that it's a function. The derivative is represented as a function. When you have this vertical line, and it can be also the right bracket like this, there's not too much difference there. You'll see them used interchangeably. It means the same thing. It means that that's the derivative evaluated at that point. So while we can say, okay, f prime at x may be some function like we found that 3x minus 2 before, if we were going to say x equals 0, then you're going to evaluate that to be negative 2. Okay? So that's that notation. We're going to have something real similar to it when we evaluate integrals as well. Okay, here's a definition now. A function is differentiable at a if f prime at a exists. That almost sounds like a trivial definition, right? I mean, if we can calculate f prime at a, then we say it's differentiable at that point. And we can say the function is differentiable on an interval if it's differentiable everywhere on that interval. Okay, so that interval may take the form of some number between two values, like we can say this is differentiable from 1 to 2, or you can say it's differentiable for x is less than 2 or something like that, or greater than 2, or you can say it's differentiable over all real numbers. And so polynomials are continuous and differentiable over all real numbers. So it's just a matter of language there. When you're saying it's differentiable, you're saying the derivative exists.
That last one's very wordy.
Is that a question or a stretch? Stretch. Okay. So then the kind of question that you'll come up with is f at x equals the absolute value of x, is that differentiable? Okay, we already know it's continuous, right? So for any value that we put in of x, if x can be any real number, we're going to get a real number out. So we know it's going to be, first of all, f at x exists for all real numbers, but if we draw it, remember it's one of the toolkit functions, we can draw it without lifting our pencil, so to speak. Every value exists, and the limit to any value exists as well. And I think I did that as an example where we show the limit of f at x as x approaches 0 is going to be 0 from the left side and from the right side. So the limit of f at x, where x equals 0, where x goes to 0, is 0. So the question is it differentiable everywhere? And so let's look at, 0 is going to be where the issue is. So let's look at just where we have x as any positive number, anything greater than 0. We'll take the limit of this thing, and where you have a positive number, the absolute value of x just equals x. There's no issue there. So we're going to find the limit of this thing, and we find that the limit equals 1. Okay, so if we look at, and I'll draw the absolute value function on the board. So if we look at any number that's greater than 0, that slope is going to be 1. Okay? Seen that before. So let's look at the negative side now. Oh, okay, well, let's say, so f at x is f at the absolute value of x is differentiable for any value of x over 0. In fact, we've found what the derivative is. Okay, so let's look at the negative side now. The absolute value of x when x is negative x, right? So if you have something like the absolute value of negative 2 is negative 2 or positive 2. So we'll calculate the limit of that, making the substitution, and we find that the limit as x approaches 0, so in other words, the slope of the line when we're negative, when x is negative, is going to be -1. And it stays at -1. So I've just shown that the derivative of f at x equals -1 where x is less than 0. So we say that then f at x equals the absolute value of x is differentiable for any value of x less than 0. Now the question is, how about 0 itself? So now this thing, if we do this limit, we come up to a dead end because we can't directly evaluate this. What we need to do is take a look at when h comes from the right or h comes from the left. Typically, when I've shown you diagrams, when we shrink that h value to get that secant looking like your tangent, it's always coming from the positive side where h is positive and it goes down to 0. But in fact, the limit exists when it comes from the left side, from the negative side as well. And so we have to look at this thing where we have h coming from 0 from the negative side and then h going to 0 from the positive side, and we find that the two limits are different, right? When it comes from the negative side, it's going to be -1. So the slope here is going to be -1, and as we come from the positive side, it's going to be 1. And since this limit then doesn't exist, the limit of the slope, the value is clear, the absolute value of 0 is 0, but there's no slope that's defined here. And kind of think about, what the slope is in terms of a tangent line. What tangent line would you place at 0? It's at a point, so you can kind of rock it back and forth, and there's no real clear single tangent line. And so that's the thing about the derivative as being a function, is that it has to give you one value. And so if we wanted to be wild and define what the derivative is here, we'd have to make it a set, not a single value. And that goes against everything that we want to know about, or everything that we want with a derivative. So then we're going to say that f prime at 0 does not exist. F is not differentiable at x equals 0. Now, in some form, I'm going to ask you about if something is continuous, is it differentiable? And if something is differentiable, is it continuous? We haven't addressed that yet, if something is differentiable, is it continuous? But this is very clear that you have a continuous function, but it's not differentiable at every point. Okay, so where do we get into trouble? Not every continuous function is differentiable. What about the other way around? Is every differentiable function continuous? The answer is yes, and there's a proof in the book that I debated whether to go through in class or not. So I looked at other calculus books to see how do they present it, because I think the one in our book is it's clear, but it's not exactly the most intuitive proof that you see. And I see that most calculus books just eliminate the issue altogether. But I think it's going to be an important point. We have this theorem that says if f is differentiable at a, then f is continuous at a. Now, the best way that I can describe to why that's true, okay, here I give you the page number of where it is in the book, is that if you look at this function, okay, we saw that this is not differentiable there, but if I take any other function, the fact that I'm saying it's differentiable means that I have a tangent at that point, right? So that would suggest several things. First of all, that f at a must exist, because how can you define what a derivative is without saying a point on the function, right? And then it also suggests that that f at a must exist here, so it has to be continuous. There's no diagram that you can draw that will show that you have a differentiable function that's not continuous. So remember, it's one way and not the other. That when you show something's differentiable, you're also showing that it's continuous. Just because you have a continuous function doesn't mean it's differentiable. So those are the two things. So what makes functions not differentiable? There's basically three conditions that we have. The first one is a corner, and so just like I had this thing with rocking, this is continuous, but it's not differentiable, right? There's no single tangent line that you can put at that point that describes what the tangent is. If you have a discontinuity, this is both discontinuous and not differentiable, because if that discontinuity happens at A, which is the slope? Is it from the left-hand side or is it from the right-hand side? Well, other than sheer coincidence, they're not going to be the same. And then the last one is where you have the tangent that's vertical. And remember, the equation of a vertical line is just x equals some constant, x equals 3. Well, the slope of that thing is not defined. It's 1 over 0. And so, since the slope isn't defined, the tangent can't be defined. There's not a value that thing that we can use to represent what that slope is. And so, with a vertical tangent, it can be continuous, but it's not differentiable. So those are your three conditions of non-differentiability. Okay, now we don't have to stick with one derivative. Okay, we can keep on taking derivatives of functions until our needs are satisfied. Very often with a polynomial, the function disappears. We just get f at some derivative equals 0. But let's look at the meaning of what a higher derivative is. Okay, so let's say I have this function f at x that describes a distance at time equals x. Okay, so this is just, at 3 o'clock I'm in Los Angeles, at 5 o'clock I'm in San Diego. It's that kind of a function. So if I look at the derivative of this, what I'm really saying is that's my rate of change, that's my velocity, right? So we've seen that in a number of examples. So what does it mean when we have, so this is the velocity, what does it mean when we have the second derivative of this distance function? So I'm taking the derivative of the derivative, and there's some ways to notate it, and I'll talk about that in just a moment. But what we're really talking about when we take the derivative of a derivative is what's the rate of change of the velocity? So what is the rate of change of the velocity? There's a word for that. Acceleration. Acceleration, great. Okay, so we call that acceleration. And in other scenarios we can have more derivatives. The thing to notice about this is in this notation here where we have d squared y over dx squared, that's not the same thing as taking the square of the square of a derivative. Okay, these two are not the same except by coincidence. Okay, so be careful. This is not a value that you can take by calculating the square of the velocity. That doesn't make sense. If you're going 50 miles an hour, your acceleration is not 2,500, right? It's something else. It could be 0. So these two are not the same. All right, that's what all right. And then higher derivatives, I want to introduce the notation. You can keep on putting primes behind it, like this would be the third derivative. The other thing is that you can put in parentheses a number, and that means the fourth derivative. All right, so f to the fourth may be the fourth power, but f to the, in parentheses 4, means the fourth derivative.